Consider the following method for creating a bivariate Poisson. It's a joint distribution for two random variables such that both marginals are Poisson. So we're defining x here to be v plus w and y be v plus z, where all these three variables here are i.i.d. Poisson with parameter lambda. So we first asked to find the covariance of x, y, and z. And so let's start by writing it down. The definition of the covariance is that e of x, so the expectation of x multiplied by y plus, should be minus the expectation of x times the expectation of y. And here we can substitute x and y and calculate, basically this is now just algebra, by substituting in what x is, what y is, and going through and calculating each and every of these terms will arrive at what the covariance of x and y is. So let's do that. There's actually a much easier way to do this, but I just want to show you how to do this by using the definition of the covariance. But the other solution would use the properties of covariance to solve for what this is much faster. All right, so expectation of, so x is, we just said x is v plus w, and y is v plus z. So v plus w, v plus z, like this. The minus expectation of v plus w, expectation of v plus z, like so. Now, these terms here, let's just calculate them and see what they are. And this requires a little bit more of effort because it will yield a polynomial term, leading us to think about the variance of Poisson, which we already know. So it's not like a super difficult thing to do. Next, let's just use linearity of expectation. So you have the expectation of v, expectation of w, like this, and then the same thing. So we retain the parentheses and just pull in the expectation function. In each of these terms here, we know that the random variables v, w, and z are i.i.d. Poisson with lambda, with parameter lambda, and we know that the expectation of the Poisson is lambda. So here we can then just say this is lambda, that's lambda, that's lambda here, and then there's another lambda. Okay, and this will end up being, so these are two lambdas, so we'll have minus 4 lambda square. Okay, let's now focus on the other term here. That can multiply in the v's and the z, so that we have here v squared, so that's v by there, v by z plus w by v, and then we have plus w by z, like this. And then we use the linearity of expectation. So we have expectation of v squared plus expectation of v z w and v. Actually, we have, let's just do the following. I'm just going to move these terms here to make a little bit more space, like this. And so what we have here as well is that we have vz. Once we have w, v, w, z. So this is, let's see, vw, vz, vwv, and we have w, expectation of w, z, like so. Right, now I'm misaligning the whole thing here. It leads to an ugly term, so let me just realign this like this. Like that. And what we have is that we know that these terms, v and z's, w of v, w and z, are independent. So we can pull out the expectations and write that this term here, as all other terms, are expectation v, expectation z, and the same here and same here, right? And these are now lambdas, so each of these terms are lambda squared. So you know that this is lambda squared, this is lambda squared, and this is lambda squared. Now the expectation of v squared, we have to rely on the definition, the variance of the Poisson. And so for that, let me write this a little bit on the right hand side here, on left hand side here. So we have, what do we have? Well, we have that the variance of v equals, running out of space immediately, like this. Let's do this. So the is v squared minus expectation of v squared, like that. Now we know that the variance of v is just lambda, right? So we know that this term here is lambda, and we know that this term here is also lambda, but we have a squared here, so that's lambda squared. So this term has to be lambda plus lambda squared. And so we write that in here, lambda plus lambda squared, like so. And then just add up the terms. So we have lambda, open up the parentheses, that's lambda. We have now 1, 2, 3, 4 lambdas, lambda squares. So that's plus 4 lambda square. And then we have the minus, you just calculated here, minus 4 lambda squared. And these terms cancel, so the final thing is just lambda. All right, that was a little bit of a long calculation, but let's just use the properties of the covariance to see how if we can do this a bit faster. So use the properties of covariance. Okay, so for that, we start writing down what, so x and y, that's what we want. And here, x and y, just by definition of the x, we define that as being v plus w. And then we define y to be v plus z. Okay, and here we can use it's almost like a cross multiplication, where we can write the covariance of v, covariance of z, covariance of w and z, covariance of w and z. And that's defined in the Blitzstein Hwang book. So that's the covariance of v, so that's that one, plus the covariance of w and z, sorry, v and z, plus now w and v, plus w and z, right? And the covariance term here, that is just the variance of v, and that we know to be lambda, right? And the rest here, the covariance of any random variables that are independent, is 0. So all these terms here are 0. So we end up with the answer that the covariance of x and y is lambda, which is exactly what we have here. Okay, so let's jump right into the next question. The next question, are x and y independent? And are they conditionally independent given v? Yeah, so they are. In fact, if we think about what the definition of independence means, that if the variables of two variables are independent, then they have covariance 0. We just calculated here that they are, there is actually covariance between x and y. So x and y are not unconditionally independent. So they are, so for first part of the question, are x independent of y? The answer is no, because we just calculated that there is indeed some covariance left here. The other part of the question is asking whether they are conditionally independent given v. Okay, so let's think about that question. So we would we can attack this problem in different ways, but we can think about the joint PMF of x and y and condition on it and see if we can retain that the left-hand side. So if if two variables are independent, we would have the following holding true, so that the joint PMF is the same thing as their marginals. So can we, and that would hold the same if we condition, right? So if we condition on WV here, then we would have basically the same thing holding here. So let's see if we can get that form that the left-hand side matches the right-hand side. All right, so let's take that. Just write down this again. P of x equals x, y, little y conditioned on v, and see what we get. So let's write, so again, x is just v plus w equals a little x, and we have y being v plus z equals y conditioning on v. All right, so now though we know that because we condition on v, we can write this capital V as little v. So we are conditioning on v like this. By doing that, we can actually remove the conditioning bar because we've already used that up and set capital V, the random variable, to a specific value. So we have little v plus w equals x, little v plus z, y, and I'm going to remove the conditioning bar because we've already used that up. And then what we have, so the random variable to the left of the equal sign, and then we have x minus v, and then we have z equals y minus v. All right, and we know that w and z are independent. And what v has done here is basically shifted by a constant. So and for any value x and y, we'll be shifting the analysis by v. So what we have here is w equals x minus v, and z equals y minus v. All right, great. So we seem to be getting at a form that resembles what we have here, but we have the variables w and z here, which is not exactly what we wanted. We need to show it for x and y. Okay, so how do we do that? Well, we can start reversing the process of what we did up here, which is that we went from x to v's and w's, used the conditioning to set this little v, and so on and so forth. We can start undoing this process by basically adding back the conditioning bar. And so basically what we do here is that we say w plus little v equals x, and then basically if I add back the conditioning bar, I haven't done anything here specific, so this is still equal, and so z plus v equals y conditioned on v equals v, right? So this is exactly what we, this thing here, by adding it back again, is exactly what we did by when we removed it. But we need to have the v's here being the random variables of interest. So now we can add back x equals x, conditioning on v, and the same with y, conditioning on capital V, like so. And this is indeed the form that we need to show to get at if x and y are independent. Okay, let's move on to the last part of the question. And here we're asked to find the joint PMF of X and Y. And we can leave that as a sum. Okay, so the joint PMF, probability of X equals X, Y equals Y. So here we need to ask ourselves, how do we arrive at this when we have basically a joint distribution between X, Y, and these other random variables? Now one way to do this is to think about the joint distribution of X, Y, and V. And why V? Well, V because it does exist in generating both random variables here, right? It's part of both Y and Z, whereas W and Z are just part of Y and X alone. So here we can then think about the joint distribution of X, Y, V, and we then marginalize over, remove basically V from this joint. And so this equals then basically this term here is the same thing as writing the using the law of total probability. X like this, Y like that. Okay, and we know that X and Y are conditionally independent. That's what we showed in B. So we can write out P, the probability of X conditioned on V, and the probability of Y conditioned on V multiplied by all this. And then we can also write that this, I mean, there's actually a limit. We're not going from V to infinity because we know that V can never be larger than either X or Y. And that's because we have X equals V plus W, Y equals V plus Z. And we see here that V, I mean, if V is larger than X, and because we know that X is an integer value, it's Poisson 0 to infinity, it can never be larger than X or Y alone. Jointly, sorry. So this basically then simplifies to the sum from V to, from 0 to the minimum, take the minimum of X and Y. Okay, and the next step here is that we know that the we can just write out what X is here. X is basically, I'm going to do it here just to save a little space. Writing, move down this little piece here like this. And so X, what is X? Well, X is, as we've said several times, is W plus V. This equals X. Now going to, again, because we have used up we have conditioning on v. This little v here looks like will equal little v, so I'm going to make it larger like that. Again, we can drop the conditioning bar when using up v, so we're left with w equals x minus little v. So that's what I'm going to write here. The probability of w equals x minus v, and then the same thing for y, which is z equals y minus v, and that whole thing multiplied by the marginal of v. Okay, and we see here that we know that this marginal is just a Poisson with the values x minus v here, and the same for z, and this is the same thing, the Poisson of a Poisson, sorry, the marginal of a Poisson. So what we end up finally with is just writing out what these things are. So keep the sum, v equals 0, x and y, and we know that the form of the Poisson is, so let's start with v because that's the purest Poisson here. The others have a subtraction of v, so here we have v squared, we have lambda v, and we have e to the negative lambda. That's just the purest of them. And then for w, what do we have? Well, we have x minus v. Like this, we have lambda x minus v, and that has the same parameter as v, and this here is the same minus v, lambda y minus lambda v, like so. Okay, and this we can simplify further if we want by drawing out the expectations, because they don't depend on the sum. And we were asked to leave this as a sum, so we're going to leave it like this. So we solved this C by this last question by marginalizing over x, y, and v. Now, what if you would, like I was thinking in the beginning, that you would just marginalize over not only v, but take the joint distribution of x, y, v, z, and w, and then marginalize over all those three variables. And that ended up being a little tricky, but let's walk through that solution again and think about what we can do in that situation if you would follow that train of thought. So I'm going to just copy this. I'm going to do a little break here and say, okay, so you have the sum now. So you're basically using the law of total probability over the joint distribution of x, y, v, z, w, right? So you sum over v, z, and w. Okay, and that this here is the same thing as thinking about basically how we generate these random variables is that we have can draw a little graph here. So basically we have x is generated by W, and is generated by V. And then Y is also generated by V, and then Z generates also Y. So here we can see that Z depends on W and V. Y depends on depends on Z and V, and then we have the marginals of W, V, and Z. W, V, and Z. Okay, so that's it looks much uglier. You need to do more calculations, and so, but what would you do here in this situation? And basically, you think about this problem in a similar way as we thought about the first solution, but when you think about the relationships between V and W and V and Z a bit more to get them accounted for. Okay, so let's do that. So we take this, I'm going to copy this thing here, duplicate it like this. I'm going to change the color to white. And we have this sum here, which is really 3 sums, and they go over the Poisson support, so from 0 to infinity. So let's start writing out, we can focus on one of these terms, this term here, and then this will be analogous. So what is x? Well, x is here, let's write out again. So x is W plus V equals x, conditioning on W, and V equals V. And here I've suppressed equal to x, just left them implicit, but basically what I meant by these equations here is basically they're equal to their little values there. Okay, so the first thing to see here is that well, so let's also write out what the values of x. So we know that x is equals to v plus w, right? And we know that y equals v plus z, which is basically an equation system here. And so we also know that by taking the joints, basically by saying we fix a value of x and y, and then we condition on whatever is conditionable upon. So here actually x is already fixed. We already know what x is. And same here, we know what x is, and so by fixing that and then condition on either v or w, so say that we condition on v, so we know what x is, we know what little x is, we can call it little x, and then we condition on little v, well then w doesn't vary freely. I mean, you can't condition on something that is unconditionable upon. So w here will be given. I mean, it's basically, w is basically x minus v w, right? So whenever you choose a value of x, and then you condition on either w or v, and say you condition on v because we can use that also for z. It's the same thing. It's basically these two events here are the same thing. So we can drop one of the conditionings here. That's what we're saying. So you choose either one of these, then you can drop the other because it's superfluous. to have there. So W, this is a random variable, still that's random variable, equals X. We can drop, I'm going to drop W, and then you can, I mean, it's basically the same thing. You can drop V as well if you want to. Well, we're going to drop W because it's easier to think about. And then here we're back in the situation where I've already used the conditioning on V. So this random variable in here turns out to be now already realized, so it's a little v. X, I wrote it as a tiny v, so you see that, and we can drop the conditioning because we've used that already. So we have W equals X minus V. Okay, and in this process for Y is the same, right? We can do that doing the same things here and arrive at this being Z equals Y minus V. Okay, and so now, and we have a sum. We have a sum here. So basically, the sum is over V, X, and W, and now we have. I'm going to write this like the following. W equals X minus V. And Z equals 1. So now it's quite similar to what we had before. And in here, we have the sum over V. Because we have a little v in here. And here, so this should be a v. And the rest of the sum, I mean, here we don't have little w. We can then pull out these sums. So we have w equals v for p of w. Yeah, and we shouldn't forget also the marginal of v also depends on v. We have another sum, which now is over z. That's where we have little z. I'm just going to write out a little w to make this explicit. And here we are summing over the support of the Poisson, and the same here. So these actually adds up to 1. This becomes 1. That becomes 1. And this term here is basically what we had before, which is this here, and the minus part is analogous over that. So this is indeed equal to that. So the whole trick is to think about what the fixing and the conditioning means and how to simplify that and get rid of one of the terms so that it adds up to the full marginal.